Now we'll come to the next property of the signal. We refer to this as the energy of the signal. So the next property of the signals we'll see is the energy of a signal. So the energy of a signal comes in handy in several scenarios. For example, let's say we want to compare two signals x of t and y of t, and we want to say that they are either equal or they are approximately equal. So if they are exactly equal, then we'll say pointwise I'll compare, and then if the pointwise comparison is equal at every single point, so for every value of t, if x of t is equal to y of t, then they are exactly equal. Now what if they are not exactly equal at every value of t, but they are approximately equal? So how do we find this approximation? Remember earlier we compared signals to vectors. This makes sense because phasors are also vectors, and then phasors are essentially nothing but one kind of signals. So how do you compare two vectors and then you say that they're approximately equal? You will just find the difference between them and then say, I'll find the length of this difference, and then you'll say that, okay, the length of this difference is very, very small. In other words, you find this difference and then you find the square of this difference, and then you will find the length in some way of this vector and then claim that, okay, this length is very, very small. So if this is really, really small for all values of t, this is approximately 0 for all values of t, then we claim that this is approximately equal. So this is what we refer to as the energy of this error. Okay? Basically this difference, or the energy of this difference, is what we'll try to compute. So the next important property that we will see of signals is what is called as the energy of the signal. So what is energy? Energy is simply nothing but the area of the signal that is present under the squared magnitude of the signal. So if I have a signal something like this, let's say this is 1 and this is minus 1. Okay. Now let's square this. If I square this, what do I get? I still get the same thing on the right hand side, but on the left hand side I'll get the squared value as such. Right? So you take the area under this signal, when you square it, you will always get the magnitude squared is always positive. You add them up and you find this area. This area is what we refer to as the energy of the signal. One nice physical interpretation is, if x of t is, let's say, the current, and let's say you're passing this through an 1 ohm resistor, then the energy that you compute through this expression is nothing but the amount of heat dissipated in it. This is one interpretation, but of course this interpretation does not work if x of t is a different kind of a signal and then you don't have a 1 ohm resistor. So if x of t is a current and you have 1 ohm resistor, then you can declare this to be the heat dissipated in it. Otherwise, this energy does not really have a physical representation or physical interpretation. But a nice way to interpret this mathematically is, you can think of this like a length of a vector, and that vector is the signal. Remember earlier we compared signals to vectors and then talked about orthogonality. So if we can talk about orthogonality, we can also talk about the length, right? So what is the length in that scenario? The length of the signal you compute in this fashion. Okay. So how length of actual signals do not exhibit this conservation of energy, meaning if I add two vectors, right? If the two vectors are in the opposite direction, the resultant vector is 0. So this vector has some length a and the opposite vector will have length minus a, or the direction is minus. So if you see the length, this will be length squared will be a square and this will be a square, but the resultant will have of length 0, right? So there is no additivity or conservation of energy. In other words, if I have two signals x of t and y of t, now we add these two signals, does that mean the energy of their addition is equal to the individual energies? Is this true? Is what we are trying to answer, and that is not true. There is no conservation of energy because this is not the actual energy. Remember, the interpretation is only for current and 1 ohm resistor. In all other scenarios, it is not the interpretation. The more sensible interpretation is to think of this as length. Okay, so which means you can see this through a very simple example. What if y of t is equal to minus x of t, right? In this case, the resultant is 0, which means this is 0, but the individual signals x of t, as you can see from this expression, energy of minus x of t is same as the energy of x of t itself, right? So this is just one number and it's the area. So since you are computing the squared magnitude, even if you take the negative of the signal, it will still have the same squared magnitude, hence the energy is the same. So you get Ex here, and this is not true, right? That's what we are saying here. So it is not true. So there is no conservation of energy. Don't treat it like the energy that we typically see in physics, and that does not apply here. But what you should be doing is treating it like a vector whose length is given by this number. So which means the Pythagorean relation holds true. What do we mean by Pythagorean relation? So if we have two vectors, let's say this is x, this is y, then their sum, which we represent like this or like this, is given by this relationship. X square plus y square is always greater than or equal to z square, where z is the additive vector, right? So this is what we know call as the Pythagorean identity. And when is this exactly equal? This is exactly equal when the angle between x and y is 90 degree, or in other words, when the two signals are orthogonal to each other, then their energies add up. Okay, we'll see why is this true. So let's say we are adding up these two signals. So the energy of this additive term is basically expanded into these four different integrals. All you have to do is just square this out. So if you square this out, you get the individual squares plus these cross terms, right? As you can see, if you remember the definition of orthogonality, this is exactly the definition of orthogonality that we had here. If these two signals were orthogonal, then these two terms will become 0, which means we will get Ex here, Ey here, and there will be Ez. So the energy of the additive term will be equal to the individual terms addition only when x of t is orthogonal to y of t. In other words, you can see this through the Pythagorean relation. So if you have two vectors which are orthogonal and their individual square lengths are x squared and y squared, then the squared length of their sum is now just x squared plus y squared, right? So that follows. So you can treat signals as if they are vectors, okay, and you can find out their lengths through the energy expression. So this gives a very nice analogy between signals and vectors, okay. So any signal which has finite energy, which means that the energy is not infinity, which means the area under the squared magnitude is not infinity, we refer to that as energy signals. Okay. All right. Let's see some examples. So the first signal here, we have the rect signal, very simple. Minus half to plus half. This is 1, which means when you compute this integral, this is from minus infinity to plus infinity, the squared magnitude squared dt. So in this case, anyway the signal's value is 0 outside minus half and plus half, and the signal's magnitude square is 1 all the time, which means the energy here is always just 1. So the energy of the rectangular signal is 1. Okay. All right. What about the energy of the triangular signal? So this is from minus infinity to infinity, the same thing. So we'll split that into minus 1 to 0. And what is the magnitude in this interval? So in this interval it is 1 plus t whole squared plus 0 to 1. In this interval it is 1 minus t whole squared dt. Okay. Let's solve this. So when you integrate this, what do you get? So we get 1 plus t squared plus 2t 1 plus t squared minus 2t. In other words, you have t plus t cubed by 3 plus t squared from minus 1 to 0, and we have t plus t cubed by 3 minus t squared from 0 to 1. So the limits, when you substitute here, you get minus 1. So 0, the first will be 0, minus of minus 1 minus 1 by 3 plus 1 plus 1 plus 1 by 3 minus 1 plus 0, right? So what is this? So what is this? So this is just 2 by 3. Okay, now let's find the energy of the other signal that we often have been using, minus 1, 0, 1. How to find the energy of this signal? We'll do the same thing. So from minus 1 to 0, we have our usual 1 plus t the whole square dt, and from 0 to 1 we just have 1. So this is equal to, we just did this evaluation here at this point, so we can just use that directly. So we got 1 by 3 there plus 1, this is 4 by 3. So one thing you can see here is you can separate this signal as the left side and the right side, and now these two are orthogonal. So you can find the energy of this portion separately and this portion separately and add them together. The same thing goes even for this triangular signal. You can find the energy of this side separately, the left hand side alone, and then multiply that with 2. You will get the energy of this side as well, because the energy here is equal to the energy on the other side. It's just the time reversed version. So you will get the energy to be equal, to be exactly the same. Okay. Now we have another signal. Let's find its energy. So this signal that we have here is e power minus t. So from minus infinity to infinity, but then anyway from minus infinity to 0, this is 0. So the energy is from between 0 to infinity, e power minus t the whole square. So what is this whole square? It's just 2 times t. This is nothing but e power minus 2t itself by minus 2, right, which is e power minus 2 times 0 minus e power minus 2 times infinity. We know that this is equal to 1 and this is equal to 0, okay, which makes the energy to be half. So as you can see, in all these cases that we have seen so far, this is finite. So this is finite, this is finite, this is finite. So all these three signals are energy signals. So all finite length signals, or all signals which have finite time, they are all energy signals. So now here we have a signal which extends to infinity but still has finite energy, which makes this also an energy signal. Now let's take an example where we have x of t to be simply equal to e power minus t, okay, which means the signal that we are considering is growing like this. On the left hand side it is growing, and on the right hand side it is decaying. Now what is the energy here? So this is from minus infinity to plus infinity, e power minus 2t dt. So you can break this into 2. So we have e power minus 2t by 2 minus infinity to 0 plus, we have just reused whatever integration we did earlier and just broke that down into the left hand side and the right hand side. The right hand side is well behaved and we know that it is just half. But what about the left hand side? So we have a problem here. The problem is that e power minus 2 times minus infinity minus e power minus 2 times 0, this is 1 but this is infinity. So which means this entire term goes to infinity. So the energy here is infinity. So this signal that we have here is not an energy signal because it has infinite energy. So now we saw an example where we had an infinite length signal which had finite energy, also an infinite length signal which had infinite energy. So it is possible to have signals which have zero energy. So a simple example is if you take x of t equal to 0, then it has zero energy, okay. So we can have signals which have zero energy, which have finite energy, which have infinite energy. All these cases are possible, okay. Now we'll see one more example. Okay, so find the energy of the signal that we have here. So it is from minus 2 to 1. So remember, all we are doing by this expression is copy pasting. So how does this signal look like? N is equal to 0. We have our usual rectangular function, and n is equal to 1. We have a shift on the right side. Let's take t is equal to 2. This is n equal to 0. This is n is equal to 1. And n is equal to minus 1. We have a shift on the left side, and this is n is equal to minus 2. This is minus 2, minus 4. Now we have to compute the energy of this given signal. How do we find the energy of the signal? One thing to note here is all of these individual components, all of these are orthogonal to one another. So because they are orthogonal to one another, you don't have to compute the entire signal's energy once again using integral. We just computed the energy of one rectangular signal, right? So that is 1. And because these are all orthogonal to one another, we know that total energy is sum of the individual 1 plus 1 plus 1 plus 1. We have 4 of them here, okay, which is just 4. That's great. So this is an energy signal because this is finite. Now what if you made this periodic? Of course, this is aperiodic. Now, what if you made this periodic? If you made this periodic, then the energy will be infinity, because you will be summing over from minus infinity to plus infinity, right? So this is infinite. So this implies not an energy signal. This is periodic. So all periodic signals will have infinite energy. This follows directly from this example, right? So you can find the energy in one period. In one period, if it is non-zero, then you can always express that as sum of multiple orthogonal signals, and whatever is the energy in one period, it will have the same energy in each individual cycles and individual periods, but there are infinitely many such periods. So this means all periodic signals have infinite energy. So all periodic signals are not energy signals. Okay? So if this is the case, then what is the property that we can use to measure or quantify periodic signals or signals that have infinite energy? So we define something else and we call that as the power of the signal.